Welcome to the compilation of 2D and 3D dynamic visualizations. My name is BrianFarrimond. My colleague Ella and I are based at Edge Hill University in a town called Ormskirk in the northwest of England. Here it is, tucked in between Liverpool and Manchester. In this presentation, I'll start with a problem our compilers are trying to solve. Then I'll show you our solutions. 3D modelling is a very important activity. It is used in science, engineering, movies, games, and so on. Traditional 3D modelling employs increasingly complex tools that produce marvellous models. Here's a typical 3D modelling tool interface. It demonstrates the complexity of these tools. The tool is extremely powerful. It can model anything with amazing realism. However, it is impossible to create these models successfully without natural ability and considerable training. The tools build from geometrical primitives, such as cylinders, boxes, and cones. Skill and experience are needed in order to identify which primitives to use to build a model and to choose the right tools to use to modify them from the dozens available. Our solution is to build models by selecting and customizing real-world components. Here is what we mean by real-world components. For this church, we can see components labelled from the bottom left: aisles, nave, columns, crossings, and so on. Here is our prototype model compiler. It is used by 10-year-old children in local primary schools. We call it Church Builder. It builds churches from components such as nave, crossing tower, transept, and spire. We build models by adding and customizing components like this. Components can have components added to them when selected. Here, the wall in blue is selected. You click on buttons to add to the wall arches, windows, columns, pictures, and so on. When we select a component in the 3D view, its attributes are revealed on the left, where we can edit them. For the nave, the attributes are length, breadth, apex height, and side height. In 1 hour, the 10-year-old children learn how to do this. Create the spine of the church, nave, crossing tower, and chancel. Add transepts to the crossing tower. Add a tower section to the tower. Convert it to an octagonal spire and change its height. Side aisles, I'll add just one. And there we are. Then the children go outside for a break. We reflected on what we had done with Church Builder and then developed the idea of compiling models and using them in compiled visualizations. We adapted the 1950s idea of compiling computer code to make programs. Early in the history of computing, it was realized that writing programs in a kind of English and then compiling or translating them was much more efficient than writing directly into this machine language that computers understand. This program is written in Fortran, containing words such as read, print, if, and so on. The Fortran compiler translates it into machine code, which can then be run. Here is an example of Java code. It is sent through a Java compiler program to make it understandable to the machine. The compiler creates the corresponding machine code, the noughts and ones, that the computer understands. This machine code program can be launched and run, for example, on a Windows PC. We have created model builders that incorporate editors and compilers. We use the editor to create model definitions. This is a fragment of a definition for a steam locomotive. The definition is compiled into geometry, which is stored in VRML files that a 3D viewer can understand. The viewer reads the VRML file and displays the model in 3D. Here is our steam locomotive builder. Component selection is achieved either by clicking in the component tree at top left, or by clicking directly on the component in a 2D view. Here the locomotive dome is selected and its attributes displayed for editing. Each builder is dedicated to building one type of object. Here is a side paddle steamer builder, a sailing ship builder, a terrain builder, this is Liverpool, a model from our railway carriage builder, and our railway signal box builder, and our cathedral builder. The different builders are collected together into two Java apps: Thing Builder for vehicles, Scene Builder for terrain and buildings. Now, a couple of video clips to show a builder in action, the cathedral builder. A cathedral starts with a single bay. We use a registered image of the elevation to get bay height and length. We add triforium and clear story. We add an arch. We modify the arch parameters using the image. And back in the 3D view, we add texture to the arcade outside and inside. We complete the triforium and clear story in the same way. We make the bay symmetrical, left and right the same, and we copy and paste 7 more bays. We shall now vault the nave. We start again with a single bay and add the vault. In the 2D view, we get the vault height above the floor and we get the apex height. In the 3D view, we texture the vault panels. We select white brick and increase the size of the bricks. We texture the wall rib, then texture the transverse ribs and the diagonal ribs, and then we add a response shaft. By default, they reach the floor. Finally, we copy and paste bays. I'll now show you the overall system for building and viewing visualizations of scenarios involving the 3D models. The model builders in Thing Builder and Scene Builder are used to build dynamic 3D models with moving parts. These models are exported and stored in the model library. We have created another Java app that we call Scenario Builder that can edit, compile, and display dynamic visualizations. The Scenario Builder visualization compiler reads a textual narrative or timetable describing the scenario to be visualized. It identifies items mentioned in the scenario and extracts their models from the model library. It uses them to build the visualization, and this can be exported. Exported visualizations can be viewed in other 3D viewers. For example, our Unity 3D viewer. Any 3D environment can host a viewer of our visualizations if it can create a scene graph whose nodes can be continuously updated as a clock runs. Here we show a typical narrative being compiled to generate the visualization scene graph and the keyframes. The keyframes record the values of the various transform nodes in the scene graph as the dynamic visualization runs. These files are read by our visualization viewers and displayed like this, or like this. We are currently focused on mechanistic operations such as railway and shipping movements. These can be visualized automatically from narratives and timetables if the operating characteristics of the railways and ships are captured in the software. I'll now show you how 10-year-old children build and run steam locomotives in a scenario. The children learn the vocabulary and grammar of steam locomotives. They make measurements from simplified engineering drawings. They use the measurements to build the locomotives in ThingBuilder. It takes the children about 15 to 20 minutes to build a locomotive after a bit of practice. Here's a cut-down version of what they do. They create a new locomotive, giving it a name. Here is the starting model. It has a boiler and just one pair of wheels. We start by selecting the running plate component and editing its attributes in the bottom left panel. And then the frame. And we skip to the final model. Locomotives have moving parts. The model compiler creates separate VRML files for these moving parts and links them together with transforms in the model's scene graph. We click on the button to build the model with moving parts. This is the dynamic model. Then we use the slider to test it. Finally, we export the model to Scenario Builder, ready for use in visualizations. The children now use Scenario Builder to create a visualization that includes their locomotive. We open the test visualization scenario in Scenario Builder. Then we edit the narrative with the new locomotive's name. And then we compile the scenario. The visualization will appear in the right-hand panel. We select the locomotive in the list of viewpoints. We move the time slider to some point in the train's journey and start the visualization running. We can export the visualization to the Unity 3D viewer. This automatically uses the OBJ versions of the models as required by Unity. We can now see the visualization running in the Unity 3D viewer. It gives us a better quality of rendering with better smoke and shadow casting. Edge Hill University has built a computer-augmented virtual environment, or cave. The Unity 3D viewer has been migrated to the cave. The children come along to the university and run their locomotives there. That's myself on the right, keeping out of the way. Here we see a pair of children watching their train approaching Bursker Bridge station. Here are some more examples of dynamic models. Here we have a steam locomotive running in the cave. You can see Alex. Alex migrated the Unity 3D viewer to the cave using Middle VR. Next we have a beam engine. Glass walls help us to see the whole movement. Here is the parallel motion invented by the Scottish engineer James Watt in 1784. Finally, we have our first ever dynamic model, a stern wheel paddle steamer. We are developing tools to build large-scale visualizations. We call these visualizations past worlds. Our prototype is based on a British railway company, the Lancashire and Yorkshire Railway. There is a society dedicated to researching its history. It provides us with specialist advice. The railway company owns the lines shown here in red across the north of England. We aim to divide it into 1 kilometre squares to model it piece by piece. As a first step, we have transcribed the 1906 passenger timetable for the railway company and used Scenario Builder to compile its visualization in 2D. Here is the running 2D visualization. When we zoom in, we can see the passenger trains running. They are the green circles. The animation has been speeded up to make it more exciting. We have prototyped the past world visualization in 3D. The prototype has 3 stations hosted online and it can be viewed through a PC app. We aim to develop a window into the past worlds on mobile devices. This is a mock-up of what we want to do. Here are some extras. In this extra, I'll show you how the movement is obtained in the scene graphs of dynamic models. Here we have part of the scene graph for the stern wheel paddle steamer. The VRML geometry is located as leaves, here, here, and here. This node controls the rotation of the wheel. As time progresses, the node's value changes, making the wheel turn. The updated value is transferred to these 2 other nodes, which control the angles made by the connecting rods. That value is processed by a reciprocal motion function to determine the correct angles for the 2 rods. In the case of more complicated mechanisms such as locomotive valve gear and the parallel motion in the beam engine, lookup tables determine the angles and locations of the various moving parts. In this next extra, I'll show you how we go about creating model compilers. Here is a fragment of the grammar and vocabulary definition for a cathedral in XML format. This is used to create the model builder containing the editor and compiler for cathedrals. Much of the code in the model builder can be generated automatically from this definition. The rest is handwritten code that creates the VRML files that will contain the model geometry. The grammar is input to a compiler, which generates the model builder library. The generated Java code is modified manually with code that creates the target object's geometry. This results in the NetBeans project for the model builder library that can be built and added to the thing builder or scene builder. The model editor inside the cathedral builder is able to save the model as an XML script. The model compiler is able to generate 3D models in VRML and OBJ formats. Finally, going back to primary school and church builder, we left the children having built their first church after 1 hour and then gone for their break. Well, they're back. They learned the grammar of churches with the help of this drawing. After the break, the children learn about arcades, clear stories, precinct walls, etc., and build this kind of thing. They are able to create tours of their churches. The children identify a path and follow it. Here we go, through the gate in the precinct wall, into the church, and finally swinging round to look back. The end. Here is a link to our website. We will be delighted if you wish to collaborate.